in our previous example, we were considering the situation where the proportion of points obtained from an alternative was a linear function, was proportional to the number of times you chose the alternative. So we're saying that on average, because of your success rate, you were getting 2 points for every 2-point shot that you made, and on average 1 point from each of the 3-point shots that you were making. And in that case, if you just think about it intuitively, there's no reason why you would shoot a 3-pointer. You're only making on average 1 point, whereas you're making more points from the 2-pointers, so you will always shoot from a 2-pointers. In that situation, the matching law would actually would agree with that, will show that indeed that's what you would do. Now, if you think of it, this is a very similar situation to the one you have in, this is something very similar to the situation that you would have in a variable, or well, not a variable necessarily, on any kind of ratio schedule. When you have two concurrent ratio schedules, essentially you're choosing between two armed bandits, right? Two gambles. One pays at a certain rate, the other one pays at another rate. And or you have to complete a number of responses on one side, and the other one you have to complete a different number of responses on the other side. Now, there's no, think about it intuitively. Why would you, if the reinforcer was effective and you were trying to get this reinforcer as soon as possible, why would you go? Why would you ever choose the alternative with the highest ratio requirement, with the schedule that required more responses for a reinforcer? You will never do that. And the matching law provides an explanation for why that's the case beyond your intuition. That's not the case, however. That situation is very different when we're talking about interval schedules of reinforcement, right? And we're going to talk about this from let me erase this part. We're going to talk about this by providing some, or bringing in this the how variable interval schedules of reinforcement, or concurrent interval schedules of reinforcement, how they operate, by providing a little bit more realism to our basketball scenario. The previous example was somewhat unrealistic because it's not taking into account that you are playing a competitive game, and that in this competitive games you're playing against an opponent, and the probability, because your opponent adjusts to your behavior and determines the rate of success of your different strategies. A particular choice, the success of a probability of a particular choice, may depend on how many times you've used that choice in the past. So, for instance, if you were to choose to always shoot 2-pointers, as suggested in the previous example, then the defense of the opponent, of your opponent team, will never worry about defending for 3-pointers. They will always stay within the 2-point area and defend against that, because that's what you're always doing. And what that will reduce the success, the probability of success of 2-pointers, and will increase the probability of success of a 3-point shot. So the fact that you are choosing one alternative more often is making it less likely to be successful on any given choice. That is very similar to what happens in variable interval schedules of reinforcement. And I'm saying variable intervals, not just interval schedules, because here an important aspect of this example is that this is not a timing exercise. In a fixed interval schedule, the probability that a particular choice or the particular response will result in reinforcement would increase over time, right? Because the closer you get to the interval requirement, let's say the interval requirement was 1 minute, the closer you get to the 1 minute, the higher the probability that that response is going to be reinforced. And in fact, it's going to be 0, the probability up to 1 minute, and after that 1 minute is going to be probability of 1. Now, with a variable interval schedule, you can arrange the random intervals that are sampled. You can arrange them in such a way such that at any given time, the probability of a response being reinforced is the same at any given time. So whether it's 1 minute has passed since last reinforcer, or 2 minutes, or 5 minutes, or 10 minutes have passed since last reinforcer, the probability that reinforcement during the next few seconds is going to be available, is going to be set up for you to collect with a response, that may be equal across all those different intervals. That's an important characteristic of most variable interval schedules. So if you think of it with a variable interval schedule, recall the feedback function for interval schedules of reinforcement. I'm going to put response rate on the x-axis, rate of reinforcement on the y-axis, and remember you got something pretty much that doesn't look like a straight line, like this. Well, this is supposed to be straight. That is the rate of reinforcement doesn't vary that much with response rate. In fact, doesn't vary at all once you hit a minimum response rate, right? That means that as you increase the response rate, the probability that any given response is going to be reinforced actually declines. The probability that any given response is going to be reinforced in a variable interval schedule of reinforcement declines as response rate goes up. Let's say if this minimum response rate you need to reach this asymptote was 10, then 10 responses may yield, I don't know, let's say 10, this is 10 reinforcers per hour. And this is responses per hour. If you make 10 responses per hour, you get 10 responses per hour, you get 10 reinforcers per hour. Then on average, each of these responses have on average about it's going to produce 1 reinforcer each response. But you go up to 1,000 responses in an hour, and you still get the same 10 reinforcers in an hour. So now each response is producing 1/100th of a reinforcer on average. The probability is really low. The proportion of reinforcers that are produced by any given response is really low. the more you respond, the lower the probability that a given response is going to be successful, it's going to be reinforced. Same thing here in the competitive basketball situation, where the more you shoot three-pointers, the lower the probability that that they are going to be successful. The defense is going to catch up to your strategy and defend for your strategy, and you'll have to accommodate. All right. Okay. So these situations in which, like the ones that I'm describing, where response rate is negatively, the response rate is negatively related to the probability of any given response being reinforced, where you have a defense that is actually accommodating to your tactic, often result in partial choices, that is, not exclusive choices, like in the previous example. And the matching law predicts the distribution of this kind of partial choices also. For instance, suppose that on a given game, let's try to illustrate this idea with an example. Suppose that on a given game you shoot successfully successful 2-pointers, you have 12, and successful 3-pointers, you only got 8. Right? What that means is that in terms of number of points, this is 24, and in terms of 3-pointers, this is also 24. 8 times 3 is 24, 12 times 2 is 24. So if you fill up this side of the equation, you have 24 over 24 plus also 24. 24 over 48, that's 0.5. You are getting 50% of your points from each of these two strategies, because you're getting the same rate of reinforcement from both choices, from both alternatives. This means that, or the matching law will indicate that you are trying to, or that you are actually trying both alternatives an equal number of times. So this has to be also 0.5. It doesn't tell you exactly how many times you tried each. It doesn't say that, but it does say that you're trying both the same number of times and you're being more successful with the 2-pointers than with the 3-pointers. You're trying that the same number of times. So if you want to think of it in terms of a concurrent VI schedule, think of it also this way. Let's suppose you have, instead of, let's move on from the basketball example. To a more abstract VI, let's say alternative A was, let me erase this too. VI 10 minutes. Alternative B is VI 5 minutes. That means that on average, reinforcement is being obtained on average roughly every 10 minutes, and for alternative A and for alternative B, roughly every 5 minutes. Think of what would happen every 20 minutes of being exposed to these two alternatives when you are sampling somewhat these two different alternatives. In 20 minutes, you would have obtained on average 2 reinforcers from here and 4 reinforcers from here. Let's run this as part of the equation of the matching law. 2 over 2 plus 4, that's 2 over 6, that's 1/3. That means that you will be obtaining 1/3 of the reinforcers from the VI 10-minute schedule. Right? That's not particularly surprising. What is interesting though is that the matching law says that this is also the proportion of responses allocated to the VI 10 minutes with respect to the VI 5 minutes. 1/3 of the responses will be allocated to the VI 10 minutes. Think of what that means. For every 3 responses, let's say this is response 1, 2, and 3, 1 response will be made to the VI 10. 2 responses will be made to the VI 5. And that makes sense because the VI 5 minutes is reinforcing the response at double the rate, no, half the time, than the VI 10 minutes. Alright, so this concludes our lecture on the matching law, and in fact concludes our lecture, this last lecture for the semester. Thanks very much for having the patience of watching over all these videos. I'll see you in class.